Welcome back. So I'm going to have another go at my code, see if I can speed up the render a little. The first thing I'm going to look at is depth testing. I'm using a sort of octree traversal to split the scene into containers. Then I'm checking through, for each ray, all the containers which it intersects. The issue is, I'm not checking those containers in any particular order, and I'm not imposing any early exit tests. Each container is an axis-aligned boundary box, and the ray intersection code will calculate the minimum and maximum t-values for any intersection. So I modified the code to return both a success flag and the minimum t-value. I can then construct a linked list of visible boxes in order of ascending distance. I could use another data structure like a heap, since it has logarithmic modification time. However, for small numbers of boxes, the extra overhead isn't necessary. What I'd like to do is then traverse the ordered list of containers and break the loop once I've checked out all the spheres in a box and intersected at least one of them. Unfortunately, this produces glitches where, for whatever reason, the edges of a far sphere cover a closer one. It turns out that my approach, although logically correct, is a little heavy-handed. Instead, I'll set a flag once I've made contact with the box, then check the box behind it, and then exit. While a little bit of a hack, this does fix the graphical errors, at least on small cases. The big question is, does this speed things up at all? Making an ordered list of boxes and deleting them for each trace definitely incurs some overhead. This method will only really shine when the number of containers gets large. We have 8,192 spheres, and thanks to SIMD, we're storing 128 spheres at most in each container, so this means we have at least 64 containers. Potentially there is some time to save in being able to stop a trace early, but only time will tell. 44 minutes! And if we look closely, we can see some graphical errors are still there. But this is still a good method because let's undo that, get rid of it. Now the next thing I'll do is tweak the pixel setting function. Using SIMD and some pointer casting, I'll set 8 bits at once. "41 minutes, that's a little better." Speeding up a screen write is good, but at the end of the day, if we make the task of writing to the screen 8 times faster, that's still not the bottleneck. The bottleneck is the fact that we are recursively tracing a high number of spheres. So I had a look at my SIMD code for the sphere intersection. Originally I wasn't quite sure how to handle the conditional code, and it actually caused me a lot of stress because conditional code is never fun. But I got a version working which runs 8 lanes at once, so it gets the 8 best spheres, and then it selects in serial among those 8 spheres. So let's see how that goes. And yeah, there we have it, 34 minutes. So that is a real, genuine speed up. Pretty excited about that. Now I'll vectorize my bounding box collision code so that I can test 8 boxes in one go. And that brings our time to the neighborhood of 29 minutes. Pretty nice. On my last video, I got the suggestion to tile the rendering rather than using scan lines. Turns out the performance was about the same, maybe a little worse. The strategy behind tiling is to keep spatial coherence. Rays in the same area tend to traverse the same path, and this opens up the possibility of better cache adjacency. For whatever reason, this didn't work out, but I'm still glad that I tried it out. I'm going to drop my flag in the sand for now and say this is where I'm at. For future, there are about 4 paths I can take. Path 1 is to use the system I have right now and just learn more about classical ray tracing theory. Path 2 is to learn about modern ray tracing pipelines, such as the NVIDIA extension for Vulkan, which natively supports acceleration structures and stakes its claim over my bank account every few years. Path 3 is to start thinking like a GPU and learn ways of implementing acceleration structures in the compute shader code. And then Path 4 is actually the most exciting. Recognize that my CPU ray tracer is pretty good, and my GPU is pretty powerful, so learn about the theory and practice of heterogeneous computing. On my previous video, a viewer brought up Cycle, a heterogeneous compute protocol by Cronus Group. The idea is that it basically lets a developer write CPU and GPU code in the same source file, and then under the hood that gets bounced down to a backend like CUDA or OpenCL in a backend independent manager. Essentially, this could be something like using the CPU like a ray tracing core, scheduling jobs for the GPU repeatedly. Ultimately, I'll go with all of these paths to some extent, and then the cross-pollination of those will, I don't know, give my life meaning or something. But anyway, for the time being, I'll research that in the background and return to the regular schedule of tutorials. Thanks for watching this, and have a great day. Bye!